So I'm Ian Wolfe. I do a weekly science and technology podcast and community radio show, Diffusion Science Radio. If you go to the website, you can listen to interviews with all of these people in the last 4 episodes. And in a conversation, sometimes they'll give you some thoughts and some information that might not have gone into the talk. So with that in mind, I'd like to start by seeding some questions, and then I'll go to the audience, and someone will come round to you if you put your hand up that you want to ask a question. So, a question that was put to me in the break, Professor Boy, if we've got aerosol viruses and bacteria and everything else in the atmosphere, particularly viruses that aren't alive and aren't dead, how long can they stay up there and just move all around the world before they're not a problem anymore?
Don't know. Look, the oceans are teeming with viruses. The air is teeming at a lower concentration. They, in order to propagate, in order to procreate, they do need cells to inhabit and take over the machinery of. So they don't have their own machinery for reproduction. They have to take over a cell. But the great majority of these viruses are just fine. We interact in a simple and non-pathological way, and medicine and people like me concentrated on the ones that cause trouble. And someone asked me about meninggal virus, and it's only actually known to have infected 2 humans and a lot of grey-headed flying foxes. And so then I read about a related virus called Hendra, which some of you may have heard of it. It's killed 2 humans, and a few more have been sick. And in one outbreak in Hendra, Brisbane, it killed in short order, within a day, a dozen horses. So it was highly transmissible and highly... Reminds me a bit... I'm going to talk too much. Reminds me a bit of The Last of Us. You catch this fungus in your brain and you're a zombie within 12 hours after a bite. Viruses don't really do that.
Thank you. So, Anna, if I could ask you the question that you seeded in your talk, if you could tell us a little bit about knots, and was it the Jones problem?
Yes, originally I wanted to speak about this in my talk, and then I realized it was too long and I didn't have time, so I planted a seed instead. And this is just another beautiful example of categorification. And it's an example that is perhaps more powerful than the one I gave. So I talked about knots and how this is a mathematical world that we study. And knots have this really mysterious invariant called the Jones polynomial. And this is a way that you can attach a polynomial to a knot. So something like 1 plus t squared plus t to the 5th. And this polynomial is really interesting because it's not obvious what it's measuring. Already we saw this in the Euler characteristic. It wasn't so obvious what this was measuring about the topological surface, but the Jones polynomial is even more mysterious. It's really not clear what it's measuring about the knot. But sort of recently there's been found to be a categorification of this in something called Kavanagh homology. And with this categorification, suddenly it's more clear what the Jones polynomial is measuring. And this tool of Kavanagh homology is really useful in other fields of mathematics. I was actually going to plant a seed for a talk that's happening at the University of Sydney next month on the 4-dimensional Poincare conjecture. And this talk, it discusses how this tool, Kavanagh homology, which arises via categorification, is actually a really promising tool at the forefront of this area of maths.
Okay, I've got a question for everybody. So, Anna, the Earth is protected by a magnetic field, but it's a very weak magnetic field. But it took 7 Tesla to protect the astronauts. Why is the difference?
Yes, thank you. Yes, the field on the Earth is a lot weaker, but it's action, not to say the distance, it's a lot longer. So it's yes, let's say that the action is on a longer distance. Instead, if we develop an active magnetic field, let's say active shielding on a transfer vehicle, this magnetic field will have a shorter action in terms of distance. It will just be around the space vehicle. So we need a stronger magnetic field. Okay, it's not just the intensity of the magnetic field, but also the space where this magnetic field exerts the Lorentz force on the charged particles. Hopefully I was clear.
Thank you. And David, so do you have to be an analytical chemist if you want to play with mass spectrometers?
Also a physicist.
Well, I got asked a question about the properties of the plasma before, and sorry, I couldn't answer it. You're better off asking her. Because the people who design and develop them, they're all physicists, correct? But to use them these days, so I mentioned in my talk that you can go to any environmental laboratory, any clinical path lab, they all have them. The majority of people using them there aren't analytical chemists. The vendors have done a very good job of basically simplifying how the software works. So when I first started, you had to understand how different components worked. Now, so the vendors done a very good job at removing that complexity. But then as a counterpoint, when something goes wrong, those people don't know what to do. So, you don't have to be an analytical chemist, but it helps.
Yeah.
Thank you. So do we have our first questions from the audience? Is anyone... Oh, there's a hand over here. We can... Over there. It's the first one I saw.
Okay.
Hello, what's your...
My question to Professor Boyd is, how does viruses penetrate cells and divide and increase numbers very easily inside the cells?
Great question. Viruses on their outer surface have spikes. So COVID has a spike protein. Influenza has different spikes called H and N. Varicella zoster, which causes chickenpox, has an E spike. All of these spikes which stick out help the virus to connect with a cell's receptor. And a receptor is something that a cell has which sticks out, which helps it to receive messages from other parts of, say, the body. So the cell receptor, for example, a thing called ACE, the ACE receptor combines with the protein S of COVID, and then that connection allows the virus to get in, and then the virus very cleverly takes over the machinery of a cell to convince the cell to make virus and not the proteins that it normally makes. So one cell can then make hundreds, if not thousands, of viruses, which then have something in their mechanism which help them to get out. So flu has two different spikes, one that gets it in, and the other one, called neuraminidase, which helps the virus to get out. And then it goes and finds another cell in your lungs and does the same thing all over again. So there's little receptors, and they're all proteins really. So the virus lock and key mechanism, it's got a lock, and it unlocks the key to a cell and gets in and takes over.
Thank you. And we've got one over here.
This is a question to David Bishop. When I did analytical chemistry at Uni of New South Wales 60 years ago, it was as dull as dishwater. And yet, when I actually had to use analytical chem to study things like particular compounds, molecules that were in, for instance, cigarette smoke. It was utterly fascinating. I would hope that after your talk, that things are totally different now, and analytical is the queen of the sciences rather than organic or inorganic, which is what most people used to fall in love with.
I would hope so too. So I think, so it obviously depends on the university you're at. So at my university, it was mentioned in my bio there, I've introduced a master's focusing on analytical chemistry technologies. Basically, of course, especially if you're living in Sydney and you want a job in chemistry, it's pretty much analytical chemistry. There's not too many synthetic chemistry jobs available. There's not too much inorganic chemistry jobs available. But if you want to go and, there's some very giant commercial laboratories out there doing analytical chemistry. And I agree. So, and we focus on hands-on learning. So that's where, actual practical skills, because that's what's, I don't work at these big commercial laboratories, but that's what they need, right? And also, if people then want to go and do research, it's better off knowing how to do something rather than, you can always look up theory later.
We've got one down there.
Cool. G'day. My name is Arfin. My question's for Professor Susanna Goodsally. Wonderful talks, everybody. This was very interesting. So one of the coolest things that's happened in the past few years or longer is the commercial growth in space.
Yeah.
And so there's all these companies, startups like the ones Edwin and I work for, who are looking at long duration voyages and all the unsolved problems there. It was awesome to see the kind of human factors challenges, but also the radiation challenge you talk of. A lot of companies are trying to plan these voyages, but they don't really necessarily understand the radiation impacts. Do you see your work evolving into kind of like a mission design as a service or having any application there?
Yeah, oh, this is a very complex question. I will try to answer based on my experience as a researcher in Australia. Okay, so okay, where do we start from? Oh yes, so then we talk about radiation protection in research is 20 years. I mean, I started with my PhD, okay, and radiation protection was always there, but it seems to me that the problem a little bit was a little to find there was not there was not a connection between the research and the company, that develop satellites, telecommunication systems, and so on. While there is, for example, in another field that is the study of the effects of radiation and damages on microelectronics. When we talk instead about space radiation protection, there is not this connection, and in my point of view, I have to say that it's good that nowadays in Australia we have the Australian Space Agency, because now they provide that environment that probably will help us to bridge this gap. Because, for example, I would love to apply for grants in Australia in this field, that is radiation protection of astronauts, but I don't know how, where, because it's research and it's not too much, let's say, it's not too commercial now, so that is a problem for some grant scheme. While instead the Australian Space Agency, the Australian government are trying instead, they are injecting, they want to create momentum in terms of industry, okay? So I am in this dilemma, let's say, in this problem, that I do something that is very research, and we have to understand how to bridge this gap, to bring the companies and the researchers to collaborate, and I would love to continue this conversation with you guys.
Fantastic. And we're still on this side of the room, and there's some more over here.
Question for Anna Romanov. I was very interested in your talk in terms of exploring equality. Got two questions. When does equality sort of disappear out of mathematics and reappear in philosophy? That question is interesting to you. I was also interested is there a very active field in research in the does not equal sign, with the one with the little stripe through it? Thank you.
Thank you. I like both those questions very much. Unfortunately, I don't really have great answers to them. I'm not. It could have become a philosophical question pretty quickly, but I'm not sure at what point it departs. So as mathematicians, we like to sort of make concrete rules and then play by those rules. And so in any mathematical world, we decide from the beginning what equals means, and then we go forward. And this question of the decision, when we decide, this is kind of laid out from the beginning. And then for your second question, I also don't know. I think it's once we have a notion of equality, then there's always that thing not holding. And if it doesn't hold, that's the definition of that symbol. But this would be an interesting prospect to see if there was more subtlety there as well. Maybe we're more interested in things being equal than being not equal.
Thank you. Oh, and we've got one at the back where the microphone is.
Right. With mature physics, what I like to see is precision. And I think with neurological disorders, it takes a long, long time to define them as to what they are. Now, a statement was made that with some of these processes, you can get good correlation between the measurement and the diagnostics of the doctor. I would think that that means that you can go straight into the measurement and diagnose a lot quicker. And the other question related to that is, if you've got a good pattern that you can produce from a measurement of someone's problem, I would presume that you can therefore compare various diseases that are on the same spectrum and find the variations and maybe improve the treatments. Thank you.
Thanks for your question. There's a couple of problems there with the technique I'm using. For starters, we're using, we need to get the brain out of people. People don't like it to give it to us while they're still alive. But it's I see where you're coming from. We are working, so we've looked at Parkinson's disease, we've looked at multiple sclerosis. We are starting a project on motor neuron disease as well. The goal is we want to understand what's going on. And once we're still trying to understand what's going on. Once you get to the understanding stage, then you can go, all right, what comes next? If we can figure out what's taking those metals there, if it is related, then you can go for diagnosis and treatment. We're still at the understanding stage. It's still very premature. There's still so much which is not known about neurology. It's, the human body is incredibly complex. I'm an analytical chemist, right? So I'm not going to pretend to be a biologist. I work with a pathologist who is a practicing pathologist at RPA with this work, and he's always fascinated by what we find. And I did say that there's clear, what we've seen, the data is showing, we are seeing these metals again and again and again in these neurological diseases. We've also seen them in cancers as well. We've seen mercury present in breast cancer and in prostate cancer. Prostate cancer. So now we can't say if the metals are there as a causative agent or are there because something else is a reactive process. So we don't want to leap to speculation. What we can say is they're there. So I'll leave it to a medical doctor to be able to...
Would you like to?
I just happened to be speaking to a neurologist who's an expert in Parkinson's disease this afternoon, and I put to her, what about the DAT scan, which people do to diagnose Parkinson's, which D stands for dopamine, which become a neurotransmitter, a signaler in the brain, which becomes decreased in certain parts of the brain in Parkinson's. And her simple answer was, It doesn't direct my therapy. It doesn't make me certain whether it is or isn't Parkinson's. It's helpful, but not definitive. It has issues with being sensitive and specific. Does it diagnose what it's meant to? Does it diagnose what it's not meant to? So this is a dilemma in medicine. We do tests all the time, and we do too many, and we spend too much money on chasing rare things. And so getting a good test is a good thing.
Okay. Oh, we've got one at the back here.
Hi, wonderful talks from all of you. I have 3 questions for 3 of the speakers today. I'll start with Professor Boyd. So you were talking about this COVID and all the pandemic issues, and that it goes and there is a mutation. So it happens one from another, and then it mutates, it becomes a new generation of disease. And you are also talking about, I think, 4 times of using of the, what's that called, the vaccination, yes. So I was thinking why this is 4 times and why this is not like, or is there a chance that we have to do it for every year once, because they're mutating and they're generating new things that we don't know what will be.
Let me answer in fairly simple terms, because I like to think in simple terms. We've gone through the Greek alphabet, and we've missed a few along the way. And what we've essentially had is every 6 months for 2 years, a new variant that escaped immunity to the old one, and therefore infected new reams of people. For the last 16 months, we haven't really had a new variant. We've had subvariants. We've had variations on the theme. But as virologists are stating, it's not different enough to cause major disease, but different enough to evade immunity and to cause new outbreaks. So we've had 4 different peaks in the last year and a bit of Omicron. Each one has been less. And that then leads me to my second explanation, which is that although it's evaded immunity, it's done so less well because each peak in numbers has been less. And the death rate has also gone down. The death rate for the first 2 peaks was very high. 15,000 Australians last year is a lot of Australians. The great majority of them were over 80 years of age, by the way. And to your third part of the question, how often should we chase this virus? Less often, and just like flu, once a year should probably be enough, and that's what I've been recommending for a while. At the same time as flu, and there'll soon be a vaccine where it's mixed in the same syringe, and that's been developed. It's being tested at the moment. And if I'm allowed to say one more thing, coronavirus and influenza virus are both RNA. They're very simple in some respects, but coronavirus has a check enzyme called a polymerase, which does ensure that its progeny are more like the parents than the progeny of flu. So flu mutates faster, and we only vaccinate newly for that once a year. So I can see us probably getting very quickly to the stage of only having a new booster for corona once a year.
Just to add to this, I had gone through parainfluenza and influenza last 2 years, once a year, and coronavirus only one time. And coronavirus thing was the COVID. I felt like nothing happened to me, and the parainfluenza, I thought I'm gonna die. Anyway, my next question is to Anna. So you were talking about, my question is almost the similar thing that the other person asked. What about when you were talking about the equal sign? What about the equivalent sign? And what about the nearly equals to sign?
Oh, you mean the other shape, so it's sort of the squiggly equals. I could have used any of those signs, really, I should say. There's nothing especially special about the straight-lined equality. In fact, usually in mathematics, what we would use is a straight line with a curly line on top. That's our normal thing for isomorphic or homeomorphic or any of these words that mean equals in different settings. So the symbol itself is not quite as important. It's just the notion of equality. And we're actually not consistent as mathematicians. We change our symbols in that context all the time. Sometimes it's one squiggly line, sometimes it's two, sometimes one straight and one squiggly. It's a little bit frustrating if you're a student.
Thank you. And the last question is for Professor David. You were talking about the Parkinson's disease and the finding mercury at a particular point of our brain. So could you please tell a bit more about it, like how much mercury and which part of the brain, and if we can know a bit more?
So the part of the brain where mercury was found amongst all samples, so that was people with Parkinson's, people without Parkinson's, and people with known mercury exposure, it's called the locus coeruleus. So again, I'm not a biologist, but it's my understanding it's at basically where the brainstem in the brainstem, so entrance into the brain. So all samples we analysed had mercury there, but the Parkinson's people, that's where we found mercury in substantia nigra. We were hearing about dopamine there, the dopamine cell death. It occurs in substantia nigra. We only found mercury there in the Parkinson's patients. There's a few other regions of the brain, pontine facial neuron and the lateral geniculate nucleus. Yes, so I'm not a biologist. I'm not going to pretend to be. The regions of the brain which were directly impacted by cell death in Parkinson's, we found mercury there. We did not find mercury there in the other samples, including people like one of our controls is someone who injected themselves with mercury for 6 months. So we know that person had mercury in their system. He's positive control. So yeah.
Okay, we've got one over here.
Yeah. Hi. First, I would like to say that the company that I work for has a value which says you should not be the smartest person in the room, like for any meeting. So I can say that I'm living the value today. So I loved every talk, and this is the first time I've attended this forum. So thank you, all of you. My question is more of an engineering, and I was talking to Professor David earlier, is that in the mass spectrometer there is a plasma, and obviously it's really, really high temperature, and a surface of the sun probably vaporize almost every material that we have on Earth. So why doesn't the whole apparatus not just vaporize with that?
Yeah, so thanks for your question. So the plasma is very well controlled. There's a defined radio frequency coil which produces the energy required to ionize the argon. There's a high flow of argon surrounding the torch where the plasma is produced to keep the plasma confined to a specific region. And then when it hits only the very tip of the plasma, which is the coolest part of the plasma, hits the actual interface of the mass spec. So it needs to actually touch it to create basically a vacuum, so we don't get outside stuff coming into the mass spectrometer. And that is either made of metals like platinum or nickel. So platinum's actually quite soft, but it's water cooled. So it's flushed with water, which is temperature of 4 degrees. That flow has to be quite high to make sure that the interface mass spectrometer stays quite cool. Thank you.
Thank you.
Professor, just a question for Susanna.
Yeah.
In relation to the trip to Mars.
Yeah.
And there's a potential, I understand, by utilising new propulsion methods to reduce the transit times by up to 75% of less than what it is now.
Okay.
I think using nuclear power. But have you heard any rumours to that effect? And
No.
is it likely to happen?
Sorry, this is not my field of research, so I'm a little bit. I know there is a lot of research in that, but I would not feel to comment. I'm not an expert. Sorry.
Just another question to Professor Boy in relation to mosquitoes. You haven't mentioned mosquitoes as a venue for transmitting viruses. Is that correct?
Oh, absolutely. Oh, absolutely. There's a whole bunch of diseases that are currently a major concern in Australia, like Japanese encephalitis, Murray Valley encephalitis, which are transmitted in the environment because we've suddenly got lots of still water in southern for extended periods and the temperature is warmer. So the mosquitoes love the water and then they bite the macropods, the wallabies, in which the virus then accumulates. And then there are mammals which get bitten, like horses and pigs, which massively amplify virus. They get much higher levels of viremia. And then when they get bitten by mosquitoes and they're in close habitation with humans, piggery workers, horse trainers and the like, they can get these nasty viruses that formerly were only in the very north of Australia. Murray Valley encephalitis, although it's named after the Murray Valley, is mainly in northern Australia. Japanese encephalitis used to never go past Cairns if it was lucky. It's usually in the Torres Strait Islands. And suddenly, in the last 2 years, these viruses are all down the east coast and over to South Australia and a real concern. And it could be because we've had La Nina for 3 years and a lot of water and a lot of mozzies, and the mosquitoes are crucial. Can I just say that that question about going to Mars, the Epstein Drive, haven't you seen the TV series?
And we've got a question here.
My question is to Anna. To what degree of certainty can you say things are equal? So there's some uncertainty, I guess, and there's the concept of the known unknowns and the unknowable unknowns and all those sorts of things that which may fit into that answer. So yeah, I'm just interested if you've looked at that sort of end of equality.
Yeah, so one lovely thing about pure mathematics is that we don't deal with the physical world. And so since all of these ideas are sort of concepts in our minds, if we declare our notion of equality to be for topological surfaces or something that we can continuously morph one into another, to show that two things are equal, we have to find some way that we can do this. But once we find it, it's there. So there's not this issue of sort of measurement uncertainty in the realm of pure mathematics. So we know things are equal if we can find sort of an equality map between them, which takes us from one to the other. And this is something, if we were actually physically making the spheres or the knots, this gets a little bit more subtle because you can ask questions, at least with the with deforming things, you sort of have to take measurements. But since all of this just is happening in our heads, we have a pretty concrete idea.
Okay, we're getting close. We've got one over here.
Another question for Robert Boyd. The pandemic has made me think how important the job of epidemiologists are, and I read this quote from a notable virologist in the history of virology in America, Hans Zinner, and Zinzer, I should say, and he was a soldier in the First World War, and he said that soldiers have rarely won wars. They more often mop up after the barrage of epidemics, and typhus, with its brothers and sisters, plague, cholera, dysentery, has decided more campaigns than Caesar, Hannibal, Napoleon, and all the inspector generals in history. How much have soldiers mopped up afterwards, considering that the Spanish flu came kind of towards the end of the First World War, and how much do you think that the whole course of humankind has kind of been more driven by epidemics than war?
Oh, you're probably right. I mean, during the war, the Great War, there was trench fever, there was, walking through and they were losing their legs to infection. There was salmonella, cholera, typhus, I think you might have mentioned. There was countless diseases killing people at the front. So, yeah, I concur. Oh, and epidemiologists are just amateur mathematicians. They'd like to be in a better place, and one day they'll be mathematicians.
Okay, so do we have another question, or is that... We have room for... No, we don't have another question? All right. So we're moving on to the next. All right,
There is a
Scott.
question here. Sorry, correct? I thought.
We've got an urgent
Two
request.
more.
Yeah, thanks. A quick one for Anna. In your topological mathematics, is there a role for multivalent logics? Do you have things that are not just equal or not equal, but you've got multiple yeses and nos? Do you have a multivalent logic role in topology?
Not that I know of in topology, but I could certainly imagine this having a place in other areas of mathematics. I mean, especially in logic, which in some sense is an area of mathematics. But I couldn't imagine how it would manifest in topology. It's sort of an interesting question. Maybe it's something to dream about.
I think you should have just answered, I'm afraid not.
Missed opportunity.
All right. Oh, and now we've got a few words here from Jonathan. Jonathan, do you want to stand up? What would you like to see?
I'd like to stand up.
All right, Jonathan.
Hello, my name is Jonathan. I am 9 years old and I go to school in Parramatta Public School. I'd like to say as much as I can about what I know in human space flight. So the first mission I'd like to talk about is the Artemis 1 mission, launched by NASA in September 2022. SLS, or Space Launch System, was launched in September 22 and went into orbit after 10 minutes after launch. When the first stage that will be jettisoned is the boosters. That boost the speed of SLS for 2 minutes until they are jettisoned to land in the ocean. Next, around 8 minutes into the flight, is the core stage. The core stage will keep firing until we are in the upper atmosphere of Earth. Then they will jettison and leave the cryogenic propulsion system, interim cryogenic propulsion system, or ICPS. The ICPS will fire for about 2 minutes to get out of the atmosphere, and then fire for another 4 minutes to get us out of Earth orbit. After the mission control has given the signal to leave Earth orbit. Then afterwards, it's going to fire a short burn that will give it speed to get out of the Earth's sphere of influence. And then afterwards, the ICPS will be jettisoned to leave the spacecraft on its own. The spacecraft will have a journey of about 2 days until it reaches the moon's sphere of influence, when it will slow down to go into a stable orbit around the moon. When it's in a stable orbit, it will change its orbit by putting it into an elliptical orbit that at one point will get really close to the moon, and then at another point get really far. For future missions of Artemis, there's going to be a lunar gateway, a lunar station called Gateway. In those next missions, Orion will dock to Gateway. Then the astronauts that are assigned to go down to the moon will transfer into the lunar lander, whereas the astronauts assigned to Gateway remain on station. Then the astronauts that are assigned for the lunar lander land back on the moon, And after a significant period of time, they will return back to Gateway when all those astronauts will go back into the Orion spacecraft. Then it will jettison and head for a course towards Earth, pulling up a few burns on that 2-day trajectory. Afterwards, when it reaches Earth's atmosphere, it will slow down again and it will jettison from the service module. Then it will point to the Orion. The Orion heat shield will be pointed towards the atmosphere. Then, as it re-enters, once the heat and plasma that forms on the heat shield as it goes through the atmosphere at extremely high temperatures and speeds, mission control will lose communication with the spacecraft because no energy, no form of communication can go through plasma. During the upper atmosphere, the first chute will deploy, slowing the spacecraft down. Then the drug chutes will deploy, slowing us down again, and main chutes deploy to slow us down to 20 kilometers per hour for splashdown. Other facts for Orion equal that the Van Allen belts that Professor Susanna said we're going to have to pass through that belt twice. Once to get to the moon and once to go back. Then the heat shield for Orion is actually the biggest heat shield ever made on NASA spacecraft. And also the ESA also helped on creating the service module for Orion. Thank you.
Thank you, Jonathan.
Well done.
So, thank you very much for your participation tonight. Same time next year? Right? Okay, same time next year, same place, and have a very safe weekend and enjoy yourselves. Thank you.